Okay, good evening. This is Professor David J. De Los Reyes. Okay, the date for tonight will be November 14, 2023. The time is 11:43 p.m. Okay, my topic for tonight will be a continuation of my AC machines, and this is now lesson number 58. We are on the topic alternator. uh, Generation, the so-called concepts and how we derive or bring out the needed voltage for our household or businesses. Okay, let's proceed. The title of the topic for tonight will be AC machines, lesson number 58. And the title of the topic, it's a little bit, it's a concept. Okay, it's a storytelling because after bringing out the formulas on how to generate voltage, there will be some concepts in which we must have to understand to familiarize ourselves in the so-called usage of the generated voltage. Okay, the title of the topic for tonight will be Alternator Coil Pitch. What is coil pitch? Because to understand the so-called generated voltage, okay, we must have to understand what is coil pitch. Because in the derived formula for generated voltage of an alternator, there are actually many parameters. Okay. Okay. Before I will discuss the concept. The corrected voltage is 4.44, the product of frequency plus the RPM of the alternator times 10 to the minus 8. This is corrected, right? This is multiplied by small letter d. And small letter d is actually the so-called correction factor. In which the correction factor is the product of capital letter K with the subscript P, meaning the pitch factor, multiplied by capital letter K with the subscript small letter d, meaning the so-called distribution factor. The formula on how to bring out the pitch factor is actually given by this equation formula here. Sine of the quantity, capital letter P, degree over 2 plus quantity. It's a sine function, so it's a trigonometry. And the distribution factor, it's a little bit complicated. Sine of the quantity, there are two terms inside, n times d degree over 2 close quantity all over. This is n again, sine of the quantity d degree over 2 close quantity. Okay, where the value n here is actually the total number of slots of the given alternator. Of any alternator we are trying to designing, okay? Divided by the number of poles of that alternator, which is always be an even number, divided by the number of phases. And for power generation, this is always three phase, right? So in here, there are so many, what do you call these, variables in the, parameters in the value of K sub P and K sub D. Actually, we needed the value n equal to, and we needed the value of P degree equal to, what's the other one? The value of D equal to. Okay? For the value of n, before I will discuss the concept, for the value of n, it is computed by just dividing the total number of strands, divide that by the number of poles, then divide that again by the number of phases. So there will be no problem on this one. We do not have to visualize this one. We'll just memorize the formula on how to get this one. Slots per pole per phase. We could compute for the value of n without visualizing, right? How about the value of P degree? We must have to visualize this one. Okay? Because if we could not visualize this one, it's hard to understand what's the one involved in the derived equation. About the value small letter d. We must have to visualize this one also. So to visualize P degree and D degree, okay, we must have to bring out the spread out. Okay, it seems we cut an alternator, we spread it out, okay, and we bring out the front view showing the tooth, slot, tooth, slot, tooth, slot, and just a single conductor on the slots. So this is a conductor, a conductor, a conductor, a conductor, a conductor, a conductor. Okay. For the value of P degree, it is this one here. Considering, before I will discuss that coil pitch over there, P degree is here. Okay. This is a conductor. Okay. This conductor here enters slot number 1. So this is actually slot number 1. Okay. It will go inside the slot. Then it will make a back turn at the back. It is this one. Okay. Then it will go back in front. Okay. So in here, it enters slot number 1. It will go to the back. Then it will go back in front, entering slot number 5. So this is actually sorry for this one. It enters slot number 1. It goes to the back. Okay, then it goes in front. It will come out at slot number 5. This is slot number 5. And the designation from number 1 to number 5 is actually that's our P degree. And the value of this is actually, just an example, 150 degrees. Okay? The distance between a North Pole, full phase, the one giving us the magnetism. Full phase is just actually a curved shape like that in which we got a winding. Okay? So if that winding is energized by an electric current, okay, it will produce a flux coming out from the pole faces. So as the armature rotates, okay, it will cut the lines of flux, so a voltage is generated. That's why our topic is alternator. Because in the so-called power generation, there must be magnetism produced by the pole phases, okay, and there should be a rotation. Okay, this winding here should rotate, cutting the lines of flux to generate voltage. So in here, P degree here is actually 150 degrees. And the normal thing, the normal degrees between a north and south pole phases is actually 180 degrees. So just in case you place windings on the slots in which the distance between the point of entering and the point of coming out is not equal to 180 degrees, okay? We call that fractional pitch. Okay, it's a fractional pitch. So, okay, hold on. So just in case the winding enters slot number 1 and it will come out at slot number 6, and if we try to compute the electrical degrees between this North Pole and South Pole, it's 180 degrees. If it's 180 degrees, okay, if it enters slot number 1 and it will go out at slot number 6, the distance in electrical degrees between coil number 1 and coil number 2 is 180 degrees. If it's 180 degrees, we call that pole pitch winding. Okay? So the definition of pole pitch winding is here. Okay? So in here, I don't have to, explain this one here, because by just visualizing these figures here, we will be knowing what is a pole pitch and what is a fractional pitch. Okay, you got it? Right? So for pole pitch, If the distance between the sides of the coil is equal to the distance of the adjacent poles, which is equal to 180 degrees, it's 180 degrees. From number 1 to number 6, this is north, this is south, it is exactly 180 degrees. Okay? If the number of electrical degrees between slot number 1 and number 6 is 180, we call that pole pitch. Okay? And there are annotations regarding pole pitch. The voltage generated in both coils are in phase. In phase. In phase meaning the voltage generated across this and the voltage generated across the second winding here are in phase. So if they are in phase, of course, they are in phase, the voltage should be double. We needed that one, okay? If it doubles, that's a good thing for us, right? So for pole pitch, if the distance between the windings is 180, okay, the voltage across coil number 1 and number 2 are in phase, so it actually doubles, right? So it's good for us. That's the significance of this pole pitch here. Okay. How about the fractional pitch? We are now discussing this concept here. How about the fractional pitch? If the distance between slot number 1 and the slot where this winding return is not exactly 180 degrees, and in here it's 150 degrees, we call that fractional pitch. Right? It is less than 180 degrees. Okay, it is less than 180 degrees. This is 150. Because a pole pitch is actually from number 1 to number 6, that's 180. So if it's only 5, it's 150. Okay? So if the winding enters here and comes out here, the type of winding is actually fractional pitch. Okay? What's next? Oh, hold on. My alarm is on. Okay, I shut off my alarm. Annotations. The one often used. And the so-called design of alternators, they don't usually do it pole pitch. Because from a north pole to south pole, that's too long, you know. Okay? It's actually something like, if this conductor enters here, it's either that it will come out here, it will come out here, it will come out here, or come out here. But to come out from number 1, then it goes out at number 6. That's full pitch, but they don't usually do that. So it could either be that it will go back at slot number 2, 3, 4, and 5, and we call that fractional pitch. Okay? But that's the one they are using this whole design of alternators. Okay. The voltage generated is approximately sine wave. Oh, it's hard to imagine this one. I don't know how we will explain this one, but according to the annotation, if it's a fractional pitch winding, the voltage generated is almost a perfect sine wave. Okay, it is almost a perfect sine wave for fractional pitch. That's according to this annotation. Maybe we could prove this one if we try to do it in the laboratory. But since we are not in the laboratory, we will assume that this concept is correct. Generated voltage for a fractional pitch is approximately sine wave. Right? The generated voltage on the two sides are not in phase. They are not in phase, meaning if the other one is plus, the other one is minus. If the other one is plus, the other one is minus. They are not in phase. Okay? Oh, that's the annotation for fractional pitch. For fractional pitch, the distance between the coils is less than 180 degrees. This is the one they usually use in the so-called design of alternators. And the voltage generated is approximately sine wave. And the generated voltage on the two sides of the coil are not in phase. Like what I said, if this plus, the other one is minus. If this is plus, the other one is minus. Okay? It alternates. That's why it's alternating current. Right? The resultant coil voltage is less than full pitch. Of course, the resultant coil voltage, meaning the voltage across this one plus the voltage across this second one, if it's a fractional pitch winding, they are not in phase. So if the other one will be at 0, the other one will be at certain angle. So if you try to add it, okay, this resulting voltage will be less than the full pitch value. Because for the full pitch value, they are in phase. So if the other one is 1 volt, of course, if we are considering 2 windings, it will be 2 volts. But for a fractional pitch, it should be less than 2 volts. That's the meaning of this. Okay? The voltages are not in phase. So if you try to add the 2 voltages, the resultant will be less than the voltage for a full pitch. Okay? That's the fifth annotation under fractional pitch. Okay? Let's try to bring out the formula and how to bring out the so-called fractional pitch voltage. Fractional pitch voltage is actually the, what they call this, pitch factor times the voltage at full pitch. Okay? This is almost, it's not equal to 1 because if this is 1, they are equal, right? So, K sub P should always be less than what the value 1. In which the value K with the subscript P is actually the pitch factor. Okay? So, if you know the full pitch voltage and you know the pitch factor, you could compute for the fractional pitch voltage. And this fractional pitch voltage, according to this, is less than E sub F, small letter f, is less than the full pitch value. The subscript is capital letter F. Full pitch, this is fractional pitch. The fractional pitch voltage is less than the full pitch voltage. Okay? Because it is to be multiplied by the so-called pitch factor, and this pitch factor is actually less than 1. Okay. It is it. So actually, we have discussed this concept already. It's easy to discuss this one because we try to visualize first on the resulting spread out figure of an alternator. Because without visualizing this on the spread out cross-section of an alternator, it's hard to imagine, right? But as soon as we try to visualize this on the figure, okay, this concept will be very easy. How about the distribution factor? Distribution factor, because in the so-called corrected factor, there is the distribution factor. This is just an annotation on the so-called distribution factor. A factor in which the induced voltage is multiplied since the coils are not all under the full phases. Okay? If the windings are all under the full phases, the distribution factor should be equal to 1. But this is hard to attain. The distribution factor meaning, it is something like this. If this is the full phase, okay, at any one moment, we could not concentrate all the conductors to be under the full phases, right? Because some are here, some are here, some are here, because it's moving, rotating, right? But just in case you could concentrate the conductors at any one moment under the full phases, okay, it says here under the annotation, the distribution factor should be equal to 1. But this is hard to attain. Because in real thing, meaning in real imagination or real thing we are doing in the design of alternators, we could not attain that all the conductors are actually under the full phases at any one moment. Some are here, some are here, some are here. That's why there is the so-called distribution factor. What's the significance of the distribution factor? Okay, it's like this. The winding directly below the full phase, okay, what you call this, will what you call this, it could take the full value of the maximum flux, right? So if he is experiencing the full value of the maximum flux, of course, the voltage will be bigger, right? But there are some windings which are not actually under the full phases at any one moment, right? So maybe they just feel the effect of the flux, not 100%. It could be 50%, 70%. That's why the voltage generated on this conductor is different from here, right? That's why there is a so-called distribution factor, right? But according to this, if we could take all the conductors, then place it under the full phases at any one moment, okay, the distribution factor is 100%. But it's not like that in real life, right? Okay? This one will, what you call this, feel the, what you call this, maximum effect of the flux. So the voltage generated will be very big. For this one, since it's away from the maximum value of the flux, the voltage generated will be different. That's why there is the so-called, if we try to take the average generated on each winding, okay, they are not equal. That's why the induced voltage here should be multiplied by the distribution factor. Okay, and this distribution factor is actually the product of K sub P and K sub D. And this is K sub D, the one we are discussing. Right? So actually there is a correction. This is the, what you call this, theoretical value. But in real life, okay, it should be multiplied by the pitch factor, okay, and the so-called distribution factor. Pitch factor, if the distance between the coils are not exactly equal to 180 degrees, there should be a value here less than 1. Okay? And in here, the value of Q sub D is also less than 1. So a less than 1 times a less than 1 will still be a less than 1. And if you try that to multiply that for the theoretical value for this induced voltage here, of course, the corrected value will be less than the theoretical value, because it is multiplied by the value of K sub P and K sub D. Okay, that's it, guys. That's the effect of the so-called pitch factor and distribution factor in the so-called voltage generation of alternators. That's why before I discuss this concept here, I try to spread out the cross-section of the alternator, showing the tool, the slats, the conductors, the number of T-degree between the windings, so we could understand what is being placed in the annotations under full pitch and fractional pitch. Okay, good evening from Los Angeles. This is Professor David Gentiles.